Today the topic of discussion is VSEPR theory and valence bond theory. Does everybody know what is covalent bond? What is covalent bond? Covalent bond is? Right, covalent bond is formed by sharing of electron between two atoms which have un, unsatisfied octet, right, or duplet, right? So everybody knows about Lewis structure. What is Lewis structure? What does Lewis structure tells us about? Lewis structure tells us about the bond, type of bond formed. Suppose chlorine has 7 outermost electron. If I start drawing Lewis structure for it, it would have 7 electrons here, and other chlorine atom would have 7 electron in the outermost shell, which will pair to give a covalent bond, right? Similarly, we can draw for HCl. Chlorine again has 7 electrons and H has single one unpaired electron, and hence it would form a covalent bond, right? But does all the atoms, all the molecules follow the octet rule? Then what is the other rule? Does hydrogen has octet? Duplet. So Lewis structure had this drawback that it did not comply with the octet rule, because we know that many atoms follow the duplet rule as well, and hence octet rule or Lewis structure had this limitation. To improvise this Lewis structure, what was the next theory to improvise the Lewis structure to explain the covalent bond formation? Then we had VSEPR theory. What is the full form for VSEPR theory? Right. It is valence shell electron repulsion, right? Valence shell electron pair repulsion theory, right? So what was the drawback of Lewis structure? Lewis theory, it would only explain the bond formation, but it did not tell us anything about the shape of the molecule. You know what is the shape of methane molecule? But does Lewis structure of methane tells us that it is tetrahedral? No, and hence the VSEPR theory comes into picture. It tells us that CH4 is tetrahedral in structure, tetrahedral in shape. So how do you find that this is tetrahedral? Or ammonia is pyramidal, trigonal pyramidal. Does anybody know how do we find out the shape of the molecule? It is very simple as picking up as a pen. It is very simple. Suppose in exam you are asked about what is the shape of SF6, sulfur hexafluoride. No, hybridization is a different concept. It comes under valence bond theory. Initially, first was Lewis structure, Lewis theory, then the VSEPR theory, then the valence bond theory, and then the molecular orbital theory. This is the hierarchy. You should remember that. Okay? VSEPR theory. What is the according to VSEPR theory? What is the shape of SF6? Any idea? How do you find out it is octahedral? Just simply add the number of outermost valence electrons. It would be 6. Number of ligands 6 divided by 2. It would give 6 what? 6 bond pairs. 6 bond pairs. So what is the shape of the molecule having 6 bond pairs? It is octahedral. Something like this. So this is sulfur, fluorine, fluorine, fluorine on the apical positions and in the square. So what was the hypothesis for VSEPR theory? It tells us about the shape of the molecule first of all, right? Unlike Lewis theory was unable to explain the shape of the molecules, right? Second point, how does it tell about the shape of the molecule? By taking into account the number of bond pairs. What are bond pairs? Which are shared between two atoms. Suppose this is HCl, right? So this is the bond pair of electron which has been shared between hydrogen and chlorine. So this is bond pair, and this which is not taking part in the bonding, this is called lone pair. And hence VSEPR theory takes into account the bond pair as well as lone pair. Which occupies more space, bond pair or lone pair? Lone pair, because it is not shared between two atoms. While the bond pair is shared between two atoms, the lone pair is centered on single atom, and hence it occupies more space. And hence, to avoid the repulsion, okay, electrons have repulsions between them. To avoid repulsion, they will try to maximize the distance to avoid the repulsion, and hence if I have a lone pair and another lone pair, it would try to repel each other, it would try to go away from each other, and hence they would try to attain maximum distance, and hence the bond angle would increase. Similarly, bond pair and lone pair also repel, but the lone pair repulsion is greater than lone pair bond pair repulsion. Hence the order for the repulsion would be lone pair repulsion is greater than lone pair bond pair, then bond pair, right? So simply, how would it tells the shape of the molecule? Now we know that it tells the shape of the molecule. It takes into account the number of bond pairs and lone pair. It also tells that the bond pair would always try to attain minimum energy. So how would it attain the minimum energy? Right. If I have some attraction for anything or repulsion for anything, it's better for me to make a distance from that person, right? Similarly, bond pair and lone pair would try to avoid the attraction, and hence they repel each other. So they would try to maintain a distance, and hence the bond angle would increase. So simply we can start from the basic molecule. Suppose if we have two atoms, you can say it AB. Suppose AB, we have AB molecule, say like CO. It would always be linear or bent or what? It would always be linear. There is no other possibility, right? Then another example is AB2, in which we have three atoms. It could have a structure like AB, B, or sorry, it would be A, B, B, or A, B, B. It could be a linear molecule or a triangular or a bent. This is called bent structure. This is linear, this is bent. Okay. Can we have an example for AB2 type molecule? CO2. Okay. How would you find out the shape of the molecule? You know, or you already know CO2 is linear in shape, but how would you find it? On the other hand, SO2 is bent or linear? So how would you find the difference? This is bent or this is linear? They look like same, CO2 and SO2? Okay, how? This is, okay, let's pick up more easy example. This would be more clear, this AB2 type of molecule would be more clear in valence bond theory, which I'll discuss in later part. Okay. For now, I can take AB3 type of molecule. It could have which type of geometry? Trigonal planar, like this. Example, BF3 or BCl3 or how would you find it? This belongs to AB3 type of molecule. What are the number of outermost electrons in boron? Boron has 3, right? 3 outermost electron plus the number of ligands are 3. Add 3 divided by 2, it would give 3, and hence we have 3 bond pair. Whenever you have 3 bond pair, the shape would be trigonal planar, and whenever you have 4 bond pair, you would have shape of tetrahedral, right? No, it is not possible. You are talking about the case of oxygen, I guess, right? Whenever the oxygen is doubly bonded, do not count it in the bond pair. If it is singly bonded, say like OH, you count it as a bond pair. Because it involves pi bond formation, which again is accountable in valence bond theory. This is a simple thumb rule. Whenever you have to calculate the shape of the molecule according to VSEPR theory, simply take the number of outermost shell on the central atom, add the number of ligands which are singly bonded and divide by 2. Then the number of bond pair would give the shape of the molecule. Simple, right? Then, yes, in that case you can neglect the double bond, because we are talking about only the shape of the molecules. I'm not concerned about the type of bond. The sigma and pi bond comes into picture in valence bond theory. VSEPR is generally for shape of the molecule, not the type of the bond. Okay? So again, if we have 5, suppose if I have 4 bond pairs, example is CH4, it has 4 outermost electrons plus 4 ligands divided by 2, it would give 4, and hence it is a tetrahedral. Another example is ammonia. It has 5 electrons plus 3 divided by 2, it would give 4, but the number of ligands are 3. So how would I place them? It would be NH, 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 and then lone pair of electron. It is like this. You draw the shape of a tetrahedral only, and you place the lone pair on the topmost position, and hence it is not tetrahedral. It is what? Okay, trigonal pyramidal. It is like a pyramid, right? Trigonal pyramidal. But you know how to come from tetrahedral to trigonal pyramidal. Okay, you have to know how do we place the lone pair. Right. What is the angle of what is the angle for tetrahedral? 109 degree 28 minutes, right? In NH3 the bond angle is, if this is like a methane, right, the bond angle was 109, but in ammonia it is 107. Okay, 107.5. Why so? Because it has a lone pair, right? This lone pair tries to avoid the repulsion between this bond pair, right? This is lone pair and this is a bond pair. This is bond pair, right? Which I am drawing as a bond. This lone pair would try to repel this bond pair, and hence it would try to maximize the distance between the lone pair and the bond pair, which decreases the bond angle from 109. 109 is the ideal tetrahedral angle, but due to presence of lone pair, the ideal bond angle has decreased from 109 to 107 degrees, right? Due to repulsion between the lone pair and bond pair, right? There is no bond here. Bond angle is between the bonds, right? So this is the bond. This has reduced from 109 to 107 degrees, right? So this you have got that. How do we get from tetrahedral to trigonal bipyramidal? Simply add the number of valence electron, number of ligands divided by 2. The number of bond pair will give you the shape, right? Next is AB5 type molecule, right? Any example? This was example of AB4, CH4 type, right? AB5 is? Okay. PCl5. What are the orbitals involved in PCl5? D orbital. Does D orbital combine? Does it? Okay. Let's take it PCl5. Number of outermost electron in phosphorus? 5. It belongs to nitrogen group, right? Plus number of ligands 5 divided by 2 gives hence 5 bond pairs. The shape should be trigonal bipyramidal. This is trigonal. This is phosphorus, chlorine, chlorine, chlorine. These are the equatorial position, right? And this is the axial position, right? Vertical position. It should have this position. This is the ideal trigonal bipyramidal shape, right? What is the shape for ClF3 and SF4? SF4. Let's take up ClF3. Right? Are you sure? ClF3 and SF4. You don't need to mug up the things. This has the number of outermost electrons 7 plus 3 give. But there are only 3 bonds, 3 ligands present, then 2 lone pairs. Then what are the possibilities to form the structure? There could be 3 possibilities. This is chlorine. Either fluorine would be at all equatorial position and lone pair would occupy a axial position, or other possibilities that all the lone pair occupy the equatorial position and other equatorial and axial position, and the other possibilities one equatorial, one axial, and the rest are placed, right? So what do you think, what should be the structure? 1, 2 or 3? Sure? What did you read? What did you learn? That lone pair repulsions, then lone pair, then bond pair. What are the number of lone pair, bond pair repulsion in first structure? It has 1 lone pair, bond pair, one repulsion, then it has 2, and then it has 3. Again, this lone pair again has 1, 2 and 3. So basically it has 6 lone pair, bond pair repulsion, right? Anything which has higher energy would be stable or not? No. Anything having minimum energy, minimum repulsion would be stable and would be possible, right? What are the number of number of lone pair, bond pair repulsion in this structure? It has 1 lone pair, lone pair, right? What are the number of lone pair, bond pair repulsion? 1, 2, 3. It has 3 lone pair, 4. 1 from this side, right? Second from this side, 2. Then there are only 2 lone pair, bond pair. You are not considering the axial repulsion because they are 90 degrees. Equatorial position are in the plane, while the axial bonds are 90 degree to each other, right? So you are not considering this repulsion, only in the in-plane repulsion. Again, this has 1 lone pair, 2 lone pair, bond pair repulsion. This has how many lone pair, bond pair repulsion? This has 2 lone pair, bond pair repulsion, and this 1 lone pair, bond pair repulsion, this 90 degree, right? So which is the most probable structure according to energetics? Second, because it has, comparative to first, second, third, it has least number of repulsions. Always remember, lone pair always try to attain the equatorial position because it minimizes the number of repulsion, right? Any doubt? Always remember, equatorial position are the favorable position for lone pairs. Lone pair would never try to attain an axial position, would never try to attain this position, right? So the probable structure is, Yes, then third would be stable. Because it has maximum number of repulsion, while comparatively third has less number of repulsion. So out of three probable structure, you can say second is the most probable one because it has minimum number of repulsion. It's a thumb rule, remember always that lone pair always try to attain equatorial position. Okay? Hmm. We are not considering actually. Basically, this is the nearest repulsion we have. This is like this is 90 degree पे, ठीक है? Then in the plane you have this bond pair. This is bond pair, right? This is bond. It has a repulsion to this, and to this. Suppose in a plane I have, suppose this is an equatorial plane, right? And I have this axial position. Then this lone pair on this tip would try to repel this corner, this corner, this corner, and this corner. Why in third we are counting a one lone pair and bond pair? What is the structure? It is chlorine. Possibility is this, right? This is the possibility, right? What are the number of lone pair bond pair repulsion according to you? This has 1, right? 2, sorry, no, we are counting repulsion for everything. I'm not counting the repulsion between axial and axial, but I'm counting the repulsion between axial and equatorial. Okay, so if this marker is on the duster, okay, then this duster tip would try to repel these four corners and not this corner because it is below the plane, right? So when it is on the plane, it would try to repel the corners of this duster. Sorry, yeah, please. Axial and equatorial. Which axial? This axial and I am counting. Okay. Can we just have a repetition of this? You have this chlorine, right? We are drawing possibilities. This is chlorine, right? First possibility is both the lone pair on equatorial position and rest are on, sorry, both the lone pair on axial position, rest are on equatorial position. Second possibility is one is on axial and the rest other is on equatorial, rest are fluorine. And the next possibility is both are on equatorial position, right? According to thumb rule, equatorial position are the most favorable position for the lone pairs. So by just looking at the structure, what do you think, which is most probable? Third one, right? I think I have changed the order, right? Okay, okay, third is the most favorable one. Just start counting the number of lone pair, bond pair or lone pair repulsion in first. According, what are the number of lone pair, bond pair repulsion in first? This is right 6. Everybody got, how do we get 6? Okay, suppose this is triangle. Suppose it is triangle, and this is the tip of the marker. It would try to repel 3 corners, right? 1, 2, 3. Similarly, नीचे से, right? It would try to repel 3 bond pairs. So basically, it has 6 lone pair, bond pair, right? How many repulsion does it have? 1, right? Then this is the bond pair. This is 1, 2, 2, and then Just 2. From this lone pair, this one, it would try to repel this axial wala, right? 1, 2. Would it repel this fluorine? No, right? We have just 2 lone pair bond pair repulsion. This one and this one. 2 lone pair bond pair repulsion. How do we get 4? This fluorine. Axial would repel this one. And this would repel this. Then just 2. Oh yes, right. 1, 2, 3, right. And then again we have 4 lone pair bond pair. What are the number of lone pair bond pair repulsion in second structure? It has majorly 1 lone pair repulsion and 1, 2 lone pair bond pair repulsion. How do 5? From axial positions. How are you counting the number of repulsions? Axial to equatorial. This is the axial position, right? This axial lone pair would try to repel these 2 fluorine, right? So basically we have 2 lone pair bond pair repulsion, and then how do this equatorial position cannot repel equatorial position, okay? And hence there would be no repulsion between this lone pair and these bond pair, okay? Basically we have just 1 lone pair repulsion. Getting? This is what is the angle between these? This is 120-degree angle, while this axial and this equatorial position has 90-degree angle. So basically lone pair repulsion was at 90-degree and 2 lone pair bond pair repulsion again at 90-degree. While this 4 lone pair bond pair repulsion are, just don't go into the angle, just count the number of repulsion. So basically the thumb rule is the equatorial position has minimum number of repulsion as compared to this. You are saying that this has 4 lone pair bond pair repulsion, but this has 1 lone pair repulsion at 90-degree, which makes it higher in energy, okay? And hence the structure 3 is most probable. Okay. Similarly, can we say about SF4? It has number of outermost electron is 6 plus 4 divided by 2, it would give 5, and hence there are again 2 possibilities. It should have a structure like this, or it could have a structure where it has equatorial position, right? There are only 2 possibilities. Either the lone pair could occupy equatorial position or the axial position, right? So what do you think? What is the most probable structure? Equatorial position, and hence this is the most favorable position. So what should be the shape of the molecule? Just assume this is like a seesaw type of structure. Can you see how does seesaw looks like? This is fulcrum, right? This is how fulcrum looks like, na? And this is seesaw. One person sits here, one person sits here. Okay? So this is a seesaw type of structure. Just forget this, okay? And just imagine that this is the fulcrum and this is the seesaw जिस पे बैठे हुए हैं. ठीक है? Can you imagine seesaw structure? Okay, this is a seesaw structure. Although it tried to have a trigonal bipyramidal structure, but eventually it turned out to be seesaw structure due to presence of lone pair in the equatorial position. Similarly, ClF3, which had lone pair in the equatorial position was supposed to have what kind of structure? It looks like it should have a trigonal bipyramidal, but it has a T-shaped molecule, T-shape. This is like T, right? This is where the ligands are present. These are the position where lone pairs are present, and hence it has no relevance as compared to where the ligands are properly present. So hence it is a T-shaped type of structure. It is a perfect T. Okay. Uh, why is the second structure more stable in? Sorry. Please explain how to find the lone pairs. What is ligand? Okay, what is ligand? Does anybody know what is ligand? Suppose I am talking about BF3, right? This is the central atom to which rest atoms combine to complete their octet or to have their noble gas type configuration, and hence I am calling this as ligand. You can also call it the bonding atoms simply. If you are not using the term ligand, simply call it bonding atoms, right? How to find out the number of lone pairs? This would come into picture in valence bond theory when we will talk about hybridization. Please explain how to find lone pair. Why first diagonal is not correct structure? First diagram. ClF3. Why equatorial position most favorable? Why is the second structure more stable? In 2 there will be 3 bond pair, lone pair, repulsion. Okay. First, I would take SF4 first. Okay? It has 6 outermost electrons plus 4 bonding atoms, right? Divided by 2, it would give 5. Basically, there are 2 possibilities: sulfur, fluorine, fluorine, fluorine. It could have a at axial position, right? The other possibility, the lone pair would occupy an equatorial position. But why do I say that this is the most favorable position? Sorry, I am saying that second is the most favorable position. Why? Can you count again the number of lone pair bond pair repulsion? What are the number of lone pair bond pair repulsion in this structure? It has 1, 2 and 3. It has 3 lone pair bond pair repulsion, while in 2 the number of lone pair bond pair repulsion are 2 lone pair. So which is more favorable? Second structure, right? Similarly, ClF3 also accounts for the lone pair on the equatorial position. ClF3, please pay attention. ClF3, number of outermost electron is 7 plus 3 divided by 2, it would give 5. We have 3 possibilities: chlorine, right? We have 3 fluorine, right? Then first possibility, both are at axial position. Second possibility, both are at equatorial position. And the third is when one is at axial, other is at equatorial.
We ourselves are placing these F and lone pair at different positions to check the most stable structure.
Yes. I'm trying maximum possibility. What are the maximum possible structures, right? Out of which, on the basis of energetics, what are the number of repulsion? I'll decide which is the most probable structure. I know a structure having minimum number of repulsion would be a stable structure, right? Count the number of lone pair bond pair repulsion in this structure. In 3. 6. I think by this time everybody knows this has 6 lone pair bond pair repulsion with the two lone pair on the axial position. What are the number of lone pair bond pair repulsion in this structure? Can I have a uniform answer? 4 or 5 or 3? It has 1, 2, right? 2, 2, sorry, upper this one, and basically 3 lone pair bond pair. Okay, this is just count the first lone pair. First lone pair would have a repulsion with this fluorine and this fluorine, 2. Then this, this would try to have repulsion with only one, यानी one lone pair bond pair. Right? What are the number of lone pair bond pair repulsion in this? Sorry. Lone pair. Right? What are the number of lone pair bond pair repulsion? 4. But out of this, what do you prefer? A lone pair bond pair repulsion or a lone pair repulsion? Lone pair bond pair repulsion, and hence this structure too would be more favorable. If I have given a choice that out of lone pair bond pair or lone pair, what would I choose on the basis of NHS? Lone pair bond pair, and hence this is the most stable structure.
The second unit is 4 because the fluorine which is at axial position will provide that repulsion to the lone pairs there, and then the lone pairs will provide to the other fluorine.
Yes. Okay? Clear? It's always a thumb rule. Always remember the lone pair would try to attain equatorial position. But there's one exception. Anybody heard of triiodide ion? It is I3 minus. It is formed by iodine plus iodide ion gives I3 minus. What is the central atom? Iodine only? Then 7 outermost electrons plus number of bonding pairs, number of bonding atoms, just 2. Other two iodine you would consider, it is like iodine and iodine. You are considering this as central atom. The other are bonding atoms, then there would be 2, but it has a minus charge. When do we have a minus charge? When it has complete lone pair of electron, then simply add 1 divided by 2. It has taken 1 pair of electrons, that's why I have added 1 in this. Okay? It would come again 5. What are the possibilities? It should have a trigonal bipyramidal shape according to VSEPR theory, but does it have a 5 bonding atoms? So how do I place iodine? It would have 3 lone pairs and the rest would be at axial position, right? This is a different case in which we can say it has a linear shape. Although I expected this molecule to have a trigonal bipyramidal shape, but it has turned out to be have a linear shape. Got it? How do we add 1? Everybody got it? Because it has complete pair of electron with it, and hence I have added this as complete 1. Sorry? Because these are the bonding atoms. Just like in BF3 you have added 3 plus 3. In I3 you have, this is the central atom just like boron, and these are the bonding atoms. So you have to add these 2 iodine. So basically 7 plus 2 and this minus gives plus 1. Okay, you cannot have this bond pairs in points or decimal. Okay, it's always a thumb rule. Any other example? AB5.
How this structure is stable then, because we said that if they occupy equatorial position, then the repulsions are minimum, and that is why the stability is achieved. So
In this case, you had a trigonal bipyramidal shape, basically iodine. You expected this to be iodine, right? So where do I place the 3 pairs of lone pair? Right, at equatorial position, and the rest on the axial position, because lone pair would never try to attain an axial position, and hence I would place the bonding atoms at the axial position. And since this is a charge structure, I would place it in a square bracket with a minus charge. I cannot avoid its minus charge. I have to show it on the structure. Okay? It's not that important, but you should remember that I expected this structure to be a trigonal bipyramidal, but it has turned out to be a linear structure. Okay? This was till AB5. What is the next? AB6. What is hybridization in IF7? IF7 and XEF4, ClF4 minus. Why are these are 3 lone pairs? Please explain again. Iodide, triiodide ion. It has 7. How do I draw triiodide? It has made by iodine plus iodide ion to give triiodide ion. Okay? In a molecule, one atom has to be a central atom around which the other bonding atoms are placed. Okay? Just like CO2. What is the central atom in CO2? C. What is the central atom in SO2? What is the central atom in methane? Carbon, right? Similarly, in triiodide also there is a central atom called iodine around which 2 other iodine are placed. So if I am saying this is the central atom, it has 7 outermost electrons plus these 2 are acting as a bonding atoms. So I would add 2. And since it has minus charge, it has complete pair of electron with it, I would add plus 1 divided by 2. It would give a 5 bonding pairs. It is showing to have a 5 bonding pairs, but from here I know it has number of bonding pairs, it has 2. So the rest are, so basically there are 3 lone pairs, and out of which, out of 5, 3 are lone pairs while 2 are bonding pairs. So this is how I get 3 lone pairs in triiodide ion. Got it? What is the type of AB6? IF7 comes under AB7 type, which I will discuss after AB6. What is the example for AB6? SF6, it has 6 outermost electrons plus 6 bonding atoms divided by 2 gives 6 only. And hence whenever we have 6 bonding pairs, the structure is octahedral. This is the octahedral shape. What is the shape for BRF5? BRF5. What are the number of outermost electrons? 7 plus 5 divided by 2 gives 6 only. Then it should have a octahedral shape. Then that means it should have a 6 bond pairs, right? So if I am drawing Br on the central atom, 4 fluorine atoms on the periphery of plane, right? Right. Other is fluorine. The next is this. This is the possible structure. Na? Again, you can say that why this lone pair is not in the plane, right? But this was case, axial and equatorial case was only for trigonal bipyramidal. It is not applicable to octahedral structure, because octahedral structure has more symmetry. Always a structure tries to attain symmetry. Okay, this is important, that lone pair should have minimum repulsion according to axial and equatorial position, but a structure always try to attain symmetry. If I place this lone pair here, then the symmetry of the molecule will get disturbed, and hence I do not want this. Any other molecule do not want this, and hence it would try to attain a axial position and to maintain the symmetry and to maintain the energetics, minimum energetics, it would try to attain an axial position. So again, do you think this is a perfect octahedral? Whenever if it had a fluorine in this position, it would have been a perfect octahedral. But since now we have a lone pair, I cannot say this is a perfect octahedral. This is a
Distorted octahedral.
no. This is square pyramidal. This is a square pyramidal. Okay. Next example is XEF4. XEF4. It has 8, right? This has 8 outermost electrons plus 4 divided by 2. It would give 6. Again, it should have an octahedral shape. But does it have an octahedral shape? Because according to this, it should have 6 bond pair. But it is showing to have 4 bond pair. So what do you think? It would have a, this is Xe, fluorine, fluorine, right? This is square bipyramidal. Square planar. So how do we account for a lone pair? When you talk about ammonia, you do not say it a trigonal. You say it trigonal pyramidal. You take into the shape of this lone pair, right? So how could you avoid this lone pair? It would form a pyramid kind of structure. Bipyramidal or square planar. It should have a square planar or a bipyramidal structure. Square planar. How many for square planar? And the rest are for? It should have a square planar structure. Next we had IF7. It is a AB7 type molecule, right? This is a AB7 type molecule. What are the number of outermost electron in IF7? 7 plus 7 bonding atoms divided by 2. It would give 7 only. Then what is the shape? What? Pentagonal pyramidal. That means draw a pentagon. This is a pentagon, right? This is I, fluorine on the apical position, then IF7, fluorine, it would give pentagonal bipyramidal to account for 7 bonding pairs, right? Pentagonal bipyramidal. Okay? Understood? So if anybody asks you for any shape according to VSEPR theory, you can tell, right? Next we have, what are the drawbacks for VSEPR theory that valence bond theory had to come into picture? कोई चीज़ तभी आती है ना नई जिसमें कभी कोई ड्रॉबैक हो तो इसीलिए नई चीज़ इंट्रोड्यूस करते हैं, राइट? So why do you think valence bond theory was introduced? To challenge or to compensate for VSEPR theory? Why? VSEPR theory, what was the drawback for according to Lewis theory? It did not tell us about the shape of the molecule. It does only about the structure, that what kind of bond is formed between HCl or a fluorine, right? It did not tell us about the shape of the molecule. But since VSEPR tell us about the shape of the molecule, but well, it did not tell us about the VSEPR theory did not tell us about the direction of the molecule, direction of the bond. I know that if there are 4 bond pairs, I have to tell the shape of the molecule to be a tetrahedral. But how does this tetrahedral shape came into picture? Does it explain how does the tetrahedral shape came into picture? VSEPR theory did VSEPR theory tell us about the shape of the molecule? How the 4 bonding pairs gives the shape of tetrahedral molecule? Does it tell? No. This was given by valence bond theory to fill that loophole, right? VBT theory, valence bond theory came into picture. Okay. What is according to VBT theory? What is VBT theory? Valence bond.
Valence bond.
Okay. All of you are aware about orbitals, right? Right? If I am talking about fluorine molecule, okay, let's take hydrogen molecule.
Ma'am, and the drawbacks of VSEPR we have to write that it did not tell the origin of the shape.
Right, origin of the shape. It did not tell us about the origin of the shape and the direction of bonds, right? Suppose I am talking about the hydrogen molecule. It is formed by 2 hydrogen atoms. So how does this hydrogen molecule form? By the overlap of valence orbitals or valence electron. Hydrogen has the electronic configuration of 1s1. So basically s orbital has a spherical shape. It has electron, right? It has electron here. This is nucleus. Similarly, this is nucleus for hydrogen and this is electron, right? These 2 orbitals come closer and they form a covalent bond, right? By the overlap of the orbitals, right? This is the valence bond theory. According to valence bond theory, covalent bond is formed by overlap of orbitals, overlap of valence orbitals, right? How many of you know about the potential energy? What is potential energy?
Energy stored in the body.
Due to position? Yes, position, due to position. Suppose I am saying, does anybody know due to bond formation energy is released or energy is absorbed?
Energy
Please. So where does this energy come from? This is the stored potential energy. Suppose this is the hydrogen atom. This is again a hydrogen atom. This is nucleus, this is electron, this is nucleus, this is electron. Okay, they are at rest. I am saying this has potential energy equal to 0. Both have potential energy equal to 0. When I am trying to form a hydrogen molecule, they would try to come too close to each other, right? So when they try to approach each other, then the electron would come in this vicinity, but nuclear repulsion would also be resulting, right? This due to these two electrons, right, which are in different orbitals, this nucleus would try to attain attraction to this electron. Initially, this nucleus has attraction for this electron only, and this nucleus has attraction for this electron. But when they approach each other, this nucleus will try to have attraction for this electron as well, while this nucleus would try to have attraction for this electron, and hence their potential energy will decrease, right? But there also are nuclear repulsions. Okay? So to avoid this, potential energy will keep on decreasing until a point is reached जहाँ पर this distance cannot be greater than the bond length. Everybody knows about the bond length. This is the minimum distance जिसके आगे वो cross नहीं कर सकते एक दूसरे को, right? Orbitals can overlap, but they cannot superimpose on each other, right? So this is the minimum distance between the two nucleus of the atoms, beyond which they cannot overlap, or beyond which they cannot superimpose on each other. So why do we calculate the, how do you calculate? Just simply This is the nucleus, right? This nucleus to nucleus distance is called bond length.
I'm asking, is there any formula or something like that?
But that is again a high profile thing which you will study later in college days. Okay, this is not relevant to you for your curriculum for now.
So it
Okay,
won't be asked.
now otherwise there are experimental techniques to study the bond length. These are basically X-ray techniques, NMR techniques. Have you heard about X-ray? I know X-ray studies, NMR studies, ESR studies. No, these are again a high level concept which you will study later on. Okay, so basically this is potential energy, right? So potential energy will keep on decreasing as soon as the two atoms would try to approach each other. This potential energy would keep on decreasing until a distance is reached which is called bond length. This is the graph. This is the potential energy. ठीक है? On y axis you always have an dependent variable. On x axis you have the independent variable which is a bond distance. Basically distance is independent. So basically potential energy will keep on decreasing when the two atoms approach each other. This energy, initially there was zero energy between for the two atoms which were at rest, right? Initially when the two atoms were separate, the potential energy for two atoms were zero, but as soon as they start approaching each other, the potential energy start decreasing, which was released as a energy of which you call as bond energy. अभी आपने बताया ना कि बॉन्ड एनर्जी रिलीज होती है जब बॉन्ड फॉर्मेशन होता है. दिस इज कॉल्ड बॉन्ड एनर्जी. बॉन्ड एनर्जी कहाँ से आती है? दिस पोटेंशियल एनर्जी जो नेगेटिव में जा रही है, जो चीज़ पहले जीरो थी लेकिन अब वो नेगेटिव हो रही है, तो बाकी एनर्जी वो कहाँ जा रही है जो माइनस में चली गई? रिलीज एज अ बॉन्ड एनर्जी. सो बेसिकली VSEPR theory and Lewis theory did not tell us why there is release of energy on bond formation. This concept was given by valence bond theory, and hence valence bond theory has advantage over VSEPR and Lewis theory, and hence this is why this is used. Okay, valence bond theory. So basically I am saying that molecules are formed when orbitals overlap, right? If I am saying that this is fluorine molecule, fluorine has the configuration as 1s2, 2s2, 2p, 4, 5, 6, 7, 3, right? Right? Is it? Fluorine has this electronic configuration. ठीक है? So basically can I write this as 2p, 6, 7, 8, 9, right? Right? This is 2s, this is 1s2. So what do you think? It should form? So what do you think? How many bonds it should form? Only one, because it has only one unpaired electron, and hence fluorine can combine with another fluorine atoms in which the 2p orbital of fluorine would combine with the 2p orbital of another fluorine, right? Similarly, if I am saying methane, carbon has the electronic configuration of 1s2, 2s2, 2p, 2, right? Then how many bond it should form? Is it? By looking at this number of unpaired electron, it is saying that it should form only 2 bonds. So why should go in excited state? टू वैलिडेट यही समझाने के लिए कि क्यों कार्बन 4 बॉन्ड बना रहा है जबकि हमें दिख रहा है कि वो सिर्फ 2 ही बनाना चाहिए. टू वैलिडेट इट्स 4 bonds. Valence bond theory suggested the hybridization concept. Right? Everybody knows about hybridization. What is hybridization?
Intermixing of
okay, of slightly different energy. That means there should not be much energy gap. Suppose if I have crayons of different size, okay, if I have used some yellow color more or green color less, right? So if I have 4 5 crayons of different length of different sizes and I mix them in a box, and when I take them out of the box, all the crayons are of almost equal sizes. Initially they were like of different sizes but near about same sizes, right? But when after hybridization, yani after mixing of orbitals, this is, you can suppose these are orbitals of different energies, right? But after hybridization, all the orbitals are of same energy, right? So if I am talking about carbon, right, I am saying it has the electronic configuration 1s2, 2s2, 2p2. Then according, if I am saying this is the ground state of carbon, then it could only form 2 bonds. But according to hybridization, this these s and p orbitals would combine and form a equivalent orbitals and form sp3 hybrid orbitals, 1s and 3p orbitals. Now these 4 orbitals all are singly occupied. These singly occupied orbitals can combine with 4 bonding atoms, or you can say 4 hydrogen atoms having single electron to form sp3 hybridization, right, to form methane, right? So basically what is hybridization? It is the mixing of orbital, intermixing of orbital to form orbitals of equal energy, right? So what was the drawback of VSEPR theory? Again we can recapitulate that it did not tell us about the direction of bonds. It cannot tell us why CH4, why methane forms 4 bonds, right? Similarly BeF2, what do you think? It has, what is the electronic configuration for beryllium? 1s2, 2s2. Then according to this it should not form any bond, right? All orbitals are filled, but it does form BeF2. So how does this form? By exciting this sulfur 2s2 electron to the p orbital, and hence these two orbital can form sp hybridization, right? This is by mixing of s and p orbitals. ठीक है? Okay, suppose all of we are know about shape of p orbitals. Suppose this is py, right? Sorry, dumbbell shape, right? This is pz or px, okay, and this is pz, right? If I am talking about methane, right, then basically hydrogen has s orbital, 1s orbital, ठीक है? If I am saying that this was 2s, this is 2p, right? This was the electronic configuration for carbon. If I am saying that these p orbitals combine with the 1s orbital of hydrogen, then simply it would look like this overlap. This is the 1s of hydrogen. But what about the 2s? It would combine with the 1s of hydrogen, then it should have a symmetrical shape. यानी वो कहीं भी हो सकता है, उसकी कोई शेप नहीं होगी, यही मतलब हुआ ना उसका, right? We all know that p orbitals are 90 degree to each other. Yes? So basically I am saying that CH4 molecule should have a shape in which the 3 carbon hydrogen bonds are 90 degree to each other, and the rest मुझे पता ही नहीं कहाँ पर बन रहा है, जो 2s और 1s के बीच में बन रहा है, नहीं पता ना मुझे, क्योंकि उसकी कोई शेप नहीं है. That is why hybridization came into picture, right? What happens on the hybridization? That 2s orbital, which was lower in energy, and 2p orbital, which is higher in energy, they mix together to form orbitals of equal energy and almost equal shape. Okay, So basically I am saying that s orbital, 2s orbital will not combine with 1s orbital as such. I am saying that p orbital will not combine as such with s orbital of hydrogen. ठीक है, I am nullifying this possibility. What I am saying that they do not combine as such, instead they first 2s and 2p orbital mix together, right? 2p x, 2p y, 2p z. They combine each other, combine with each other. Suppose this is the p orbital having positive and negative lobe. It would combine with the 2s orbital, right, to form a this kind of structure, right? So basically if I am saying 2s orbital is combining with just 2p orbital, if I am saying it is a sp hybridization, then only one s orbital and one p orbital will hybridize. That means it would have a structure like suppose two bigger lobes with two small lobes. If this is positive, this is negative, and this is positive, this is negative. This is a sp hybridized lobe. And now this will combine with the s orbital of hydrogen. If suppose this is beryllium, right? Beryllium, BeF2 was example of sp hybridization. Remember what was the electronic configuration? 1s2, 2s2, right? That means it would excite one electron from s orbital to p orbital. It would become 2s1 and 2p1, and hence I am saying it is a sp hybridization. Due to sp hybridization, due to mixing of s and just one p orbital, the orbital will not look like individually different, but they will look like this bigger lobe and two small lobes. Now these lobes can combine with the fluorine. Fluorine has the orbital of p orbital. Fluorine has outermost orbital of p shell, right? Then it would combine with the p orbital on both the sides. This bigger lobe is the hybridized orbital of beryllium, in which will combine with the p orbital of fluorine.
After this combining with such an element in which it has to combine with the S1, so the smaller lobes will be there.
Sorry.
मैम अगर किसी ऐसे से कंबाइन कर रहा है वो जिसमें कि S से वो कंबाइन हो रहा है, तो स्मॉलर लोब से अटैच होगा.
नहीं, it would always positive lobe would always prefer a positive lobe. S orbital is always symmetrical. It is always positive only, or it is always negative only. We always take it as positive only. So if I am saying that this central atom has some sp hybridized lobe looking like this, then it would combine with the s orbital simply like this. Yes, bigger lobe only. These are basically inside lobe which do not participate.
Then why are we showing them?
Why are we showing? Because this is the bond.
No, inner lobes.
Why p orbital is dumbbell shape? Why p orbital is dumbbell shape? Anyone? Any idea why p orbitals are dumbbell shaped? What does dumbbell look like? Dumbbell. Basically इन जिम आप जाते हो ना, मतलब आप नहीं जाते होगे, जिम में जो लोग डंबल उठाते हैं बॉडी बिल्डिंग के लिए, ऐसे होता है ना डंबल, राइट? तो डंबल शेप क्यों होते हैं पी ऑर्बिटल्स? ऐसे ऑर्बिटल्स स्फेरिकल क्यों होते हैं? व्हाट इज द शेप ऑफ डी ऑर्बिटल्स? डबल डंबल, समथिंग लाइक, राइट? दिस इज लाइक dxy, or similarly dxy, dyz and dxz, right? Or dz square and dx square minus y square. ठीक है? Why do we have different shapes? This shape is based on the experimental findings. by X-ray studies. Okay, to minimize the number of repulsion. Only suppose this is s orbital. S orbital can only occupy only how many electrons? 2 electrons. Similarly, it's like this is the nucleus, okay, around which there are various shells. I am saying that the first shell has only one s orbital. It can occupy only 2 electrons. And as I go away from the nucleus, I can have more number of orbitals, right? It could have a spherical and a dumbbell shaped p orbital, but the shape of the orbital is dependent on experimental findings. You cannot say why it is dumbbell shape. Okay, this is again an experimental finding. And then again in the another lobe you find s, p and d orbitals, right?
On that previous one, why do we represent that inner orbital in number particles?
But you have to suppose this is the dumbbell shaped p orbital, right? If it is combining with the s orbital, right, you cannot, this is positive lobe, this is positive lobe, this is negative lobe, you cannot avoid this negative lobe. Majorly this part, this hybridized part, this is major part which is taking part in the bonding.
Ma'am, then the structure should be like
Yeah,
एक मिनट. बस इस साइड पॉजिटिव और नेगेटिव छोटा होना चाहिए. डबल क्यों बनता है कि इस साइड भी एक छोटा नेगेटिव और इस साइड भी एक बड़ा पॉजिटिव? वो दो
इस
P
टाइम
को
बड़ा
combine-
पॉजिटिव नहीं है, दिस इज जस्ट अ नेगेटिव.
आपने जो बनाया था उसमें दो पॉजिटिव और बीच में दो छोटे
हम्म,
नेगेटिव थे,
हम्म.
तो ऐसे क्यों?
ऐसा क्यों? मिक्स होने के बाद द ऑर्बिटल्स लुक लाइक दिस. ठीक है, ये सिर्फ आपको
दो P
समझाने
mix
के लिए. हाँ, दो पी मिक्स नहीं हुए, पी सिर्फ एक ही मिक्स हुआ है. सपोज दिस इज हाउ अ पी ऑर्बिटल लुक्स लाइक. ठीक है, positive and negative. I am combining it with the s orbital. Basically, it would now look like this is hybridized look. Okay. Similarly, if I am saying there are, this is sp, this was sp hybridization. If I am saying sp2, that means there are 3 orbitals combining. So basically, I would have 3 bigger lobes and small lobes inside it, plus plus minus minus. Okay, this is how after mixing the orbitals look like. Hybridization is a theoretical concept, it is not true, it is just a hypothesis to account for the shape of the molecule or direction of the molecule. This is how we assume. अगर अच्छा ठीक है, अगर 4 बॉन्ड बन रहे हैं तो ऐसा हुआ होगा. ठीक है, इट्स किसी ने देखा नहीं है हाइब्रिडाइजेशन को, इट इज जस्ट अ कंसेप्ट. Because I am combining sulfur, I am combining s orbital to be a positive lobe,
Unless it is the negative, and then negative would be bigger and
right, vice versa. But always I consider s orbital to be a positive lobe, right, because it is spherically symmetrical. ठीक है, this is how sp3 hybridized orbital will look like. These are 4 orbitals and they would look like a tetrahedron. This is how sp3 hybridized orbitals will look like. How we can decide that s orbital is positive or negative? Why does inner lobe does not participate? How do we decide s orbital is always positive?
spherically
It is spherical symmetrical. I can assume it to be a negative or a positive.
by convention we take
By convention we take it as positive only. Why inner lobe is not participating in the, because basically if I am saying plus and plus is combining, that means the other rest part minus this has major, sorry, if I am saying that this is the plus plus part is combining, then this part would attain a bigger portion in the orbital. You cannot say that this has nullified, you cannot say that it is not participating, you cannot deny that the orbital was initially dumbbell shape. If it is combining with the s orbital, I cannot say that the dumbbell shape has changed. The dumbbell shape would remain, but it would not participate in the bonding. It is participating in the bonding, but not in the overlap case. It is not directly overlapping with the hydrogen orbital, with the s orbital of hydrogen, but it is participating in the bonding directly or indirectly. If I am saying that the s orbital is combining here, then I cannot say that this is not the part of the p orbital. It is a part of the p orbital, but it is not directly overlapping with this s orbital. Okay, it is not that minus lobe is not taking part in the overlap or bond formation. It is taking part, but obviously anything, if I am trying, if I am saying that there has to be a bond formation, then the positive lobe has to combine with the positive lobe. If I am saying that the positive lobe combined with the negative lobe, then there would be a nodal formation. Have you heard about nodes? What are nodes?
Place where the probability of finding the electron is
Negative, right, where the probability of finding the electron is negative. If I am saying that this is the possibility of placing a electron, यहाँ पर इलेक्ट्रॉन है और आई एम सेइंग कि यहाँ पर इलेक्ट्रॉन नहीं है, सो यहाँ पर अगर इलेक्ट्रॉन नहीं है तो वो यहाँ पर होगा, राइट. सो अगर यहाँ पर एक कंबाइन करेंगे तो क्या बनेगा प्लस माइनस की वजह से? अ नोड. नोड मीन्स where there is no possibility of finding electron. Okay. You are confusing. Okay. Positive. When I was saying that the positive lobe was combining with the positive lobe, that was for hybridization. If I am saying, okay, suppose this is example of fluorine molecule. This is the 2p orbital, this is the 2p orbital. ठीक है? This is combining to form a fluorine bond, right? Then if I am saying this is the positive lobe, this is the positive lobe, it would try to form, it would try to overlap where both the lobes are positive, where the probability of finding of electron is maximum. And in this overlap there would be 2 electrons. If I am saying that the positive lobe combining with the negative lobe, that means there would be a node formation. Plus minus would try to negate each other, right? That means there would be no bond formation. When there is an overlap and there are in between the overlap there are 2 electrons, there is a bond formation. If I am saying that the positive is combining with the negative, then there would be a node formation. That means there would be no bond, and hence where there the possibility of finding the electron is 0 or negligible.
this type of combination, what will be the shape after?
It would be just a node. Just suppose if this is, it would look like, if this is the p orbital minus plus, right, then it would look like smaller lobes. Yeah, it is called nodal plane. Will get bigger. It would become a shape like, right, like this. Okay. Very much maths. Sorry. If I am saying positive is combining with negative, node will form, and this would form a small lobes, and this would be of normal shape. I think I have drawn too big. It would be of normal shape, right? If I am saying that the positive lobe is combining with the positive lobe, then the shape of the middle lobe would increase. That's it. And this is the resultant, this is basically a bond. So valence bond theory is basically the idea that bond is formed due to overlap of valence orbitals, and these valence orbitals basically they hybridize to form the bond. Otherwise you cannot account for the methane forming 4 bonds. Otherwise you cannot account for carbon forming 4 bonds. You cannot account for beryllium fluoride to form 2 bonds. Similarly, BCl3, you cannot say it can form 3 bonds. It only because of valence bond theory and hybridization that you can account for the bond formation. So basically, covalent bond has 3 or 4 theories, I would say. First was Lewis theory, right? Then you had VSEPR theory, right? Then valence bond theory, and then you have molecular orbital theory. So this is the hierarchy. You cannot account for hybridization in VSEPR. You will only talk about hybridization when you are talking about valence bond theory. Okay? Can we take more example for valence bond theory? Any molecule? Any molecule you want to discuss? Ammonia. Okay. Okay, let's discuss methane first. This is, I think we have already discussed. This is 2s2, 2p2. This is in ground state. I'm talking about excited state, right? 1, 2, 3, and this is 4. This is the sp3 hybridized, and hence how would the molecule would look like after overlapping? How would the sp3 hybridized orbitals were looking like? This was how the sp3 hybridized look like. So if I'm saying this is CH4, these sp3 hybridized orbitals will overlap with the 1s orbital of hydrogen, 1s orbital of hydrogen, 1s orbital of hydrogen, and 1s orbital of hydrogen. That's it. So basically this is how methane is formed, right? Yes. Okay, you are noting down. Done? Ammonia. Yes, ammonia. Uh, Ammonia has electronic configuration of 1s2, 2s2, 2p3, 1s2, 2p2, 2p3, right? This is in ground state. Excited state would have same, right? So if I am saying it is forming NH3, it should form a trigonal pyramidal. It would form a sp3 hybridized state, right? I would redraw actually. Although the electronic configuration is same, but I am redrawing it to show that this is an excited state. Okay? These 3 orbitals will participate in the bond formation, right? And this would remain as a lone pair, right? So basically it would be nitrogen. It would look like it has lone pair, and this is, right, hydrogen, hydrogen, and hydrogen. Okay, this is how we get trigonal pyramidal structure. Okay, the question is, does d orbitals participate in hybridization? Anyone? Are you sure? What is hybridization? Hybridization is intermixing of orbitals of almost equal energy. But does d orbital has equal energy as of s and p orbital? It is way too higher than s and p orbital. So what should we do? Then according to this, d orbital should not participate in hybridization, and whatever you have heard so far of sp3d hybridization should nullify. But there is something which happens. You know about sp3d hybridization, it does happen. So how can you account for sp3d hybridization? Exception. How do we account for the exception? Okay, we have learned the example of PCl5, right? I am saying, what is the electronic configuration for phosphorus? Outermost 3s2. Are you sure? 3p3. Okay, right. 3p3, right? What is the structure for this? Trigonal bipyramidal. That means 5 bond pairs. So accordingly, what should be the hybridization? sp3d. How do we find it is sp3d? Similarly, on the basis of the bond pairs, right? These are 4, 5. 1s, 3p, 4, and this is 5. Okay? But how do I say that this hybridization takes place? I am saying d orbitals are way too higher in energy. How would they mix with s and p orbitals which are very less in energy? It is possible only because chlorine is highly electronegative. So what if it is highly electronegative? Okay, chlorine can easily gain electrons. That means if I am drawing the structure of PCl5, right, then these bond pairs will be more towards phosphorus or chlorine. Chlorine. That means phosphorus would attain a positive charge or a negative charge? Positive charge. If it is attaining a positive charge, the d orbitals would try to shrink. How would they shrink? If I am saying chlorine is highly electronegative, it would try to attain the bond pairs towards itself, due to which the phosphorus would tend to have a positive charge. It would fall short of electrons, and hence nucleus would try to attract the remaining electrons toward itself, right? Sorry, I am not saying that there are no electrons in the d orbitals. What is the outermost electronic configuration? It is 3s2 3p3, but there are no electrons so far in the d orbitals. But I am saying that it happens that there are electrons in the d orbital. और वो कब होगा? जब I am saying कि यहाँ पर mixing हो जाए, तभी वो possible हो पाएगा. तो mixing कब होगी? ड्यू टू हाइब्रिडाइजेशन. लेकिन हाइब्रिडाइजेशन हम कह रहे हैं कि सिर्फ इक्वल, ऑलमोस्ट इक्वल एनर्जी वाले ऑर्बिटल्स में ही होती है. तो हम क्यों कहेंगे कि डी ऑर्बिटल मिक्स करेगा, जबकि जो बहुत ज़्यादा हाई एनर्जी है वो इसीलिए करेगा बिकॉज chlorine is highly electronegative. It will try to attain bonding pairs electron towards itself, and hence phosphorus would attain a positive charge. That means its d orbitals would try to shrink. जितने भी बचे हुए इलेक्ट्रॉन्स हैं उसको वो खुद अपने पास रखने की कोशिश करेगा. If I am saying कि suppose if I am talking about sodium, and if I am talking about sodium ion, which has a bigger size? Why? What are the number of electrons here? Number of protons? What are the number of electrons here? Protons. Attraction is more in Na plus, right? Similarly, if I am saying that chlorine will try to attain electron pair toward itself, then phosphorus would try to attain a positive charge, जिसकी वजह से उसका, जैसे similarly सोडियम का साइज श्रिंक हो गया, इसी तरीके से फॉस्फोरस का साइज श्रिंक हो जाएगा. और श्रिंक कैसे होगा? बाय श्रिंकिंग द साइज ऑफ द ऑर्बिटल्स, ड्यू टू विच डी ऑर्बिटल का साइज श्रिंक हो गया, और जिसकी वजह से अब डी ऑर्बिटल इन ऑर्बिटल्स के साथ मिक्स कर पाएगा. जब उसका साइज कम हो गया, उसका मतलब उसकी एनर्जी भी कम हो गई है, राइट? सो इफ आई एम सेइंग कि अगर ज़्यादा इलेक्ट्रोनेगेटिव कोई आयन आ जाए उसके पास तो उसका साइज कम हो जाएगा और वो s और p ऑर्बिटल्स जैसे ऑर्बिटल्स के साथ मिक्स कर पाएगा टू फॉर्म हाइब्रिडाइजेशन। साइज कम होने से एनर्जी कम हो जाती है। कोई भी चीज़ बड़ी होगी उसके अंदर एनर्जी ज़्यादा होगी, राइट? इफ आई एम सेइंग कि इफ आई जंप फ्रॉम दिस पोजीशन, is it possible that I will remain in the air for long? I would try to attain stability by remaining on the ground. So if I am saying anything which is bigger, it would always have a higher energy. Okay? Please draw the structure of XeO2. Are all the bonds PCl5 same? Why water is having V-shaped structure? Okay. First I'll take up these questions. XeO2, water, V shape, and then other question was? No. PCl5, right. In PCl5 there are two types of bonds. Two are axial bonds and three are equatorial bonds. Obviously they have different bonds. Sorry? Basically we have two axial and three equatorial position. ठीक है? What is the shape of XeO2? It has number of 8. Here the oxygen is doubly bonded. How would you account if the oxygen is doubly bonded or singly bonded? If it is negative, that means it is like OH. Anything, जब भी ऑक्सीजन आपको दिखे इसी तरीके से तो इसका मतलब वो डबली बॉन्डेड है, until unless उसके साथ OH नहीं है, ठीक है? So you always take oxygen as doubly bonded. So यहाँ पर I am not taking doubly bonded oxygen, ठीक है? I am taking only the 8 electrons of this central atom and I will not add any contribution from the bonding atoms. It would be 4. So basically what is the probable shape for tetrahedral? So basically it should have a structure like this. Right? और कोई possibility नहीं है? Right? This is the shape for XeO2. Right? Any doubt? Yeah? No? Too much of repulsion between these two lone pairs, obviously due to which the ideal angle which happened to be 109 degree, it would decrease to some 90 degrees or 104, whatever. It could be 90 degrees as well, because there are two lone pairs, they will try to repel each other, and again this lone pair and bond pair would try to repel each other. Exact, I don't know. 104 would be too high. I think it should around 90. It should around 90. But it would be less than the ideal tetrahedral angle. Okay. What is the shape of H2O? Oxygen is, what is the central atom in H2O? Oxygen. Oxygen has number of outermost electrons 6 plus 2 divided by 2, it would give 4. That means it should again have a tetrahedral shape. So if I start drawing OH, OH, it means only two bond pairs and the rest two are lone pair. And hence it is again another case of tetrahedral. This is the order. CH4 is the ideal case. Then if I introduce one lone pair, it would be a case of ammonia. If I again introduce one more lone pair, it would be case of H2O. This is tetrahedral. This is trigonal pyramidal, and this is bent shape or V-shape molecule. Okay, this is how it looks like. This is why the water is bent shape or V-shape molecule. Okay, again I want to ask, is this concept of dehybridization is clear? Why d orbital participate in hybridization? although they are bigger in size and higher in energy, but due to presence of highly electronegative atoms, d orbitals shrink or contract in size, due to which
person reduces as they participate in hybrid bonding.
I'm not saying they are forming cation. No. Is PCl5 a cation? Whenever you talk about charges, it is not necessary you are talking about ionic species. Okay? You're not talking about ionic species. I'm just saying that when this PCl5 forms this bond pair, these are the bond pairs, right? These, due to highly electronegativity of chlorine, these bond pairs are pulled towards the chlorine. That means they are here. Rather than in between, they are more towards the chlorine, due to which the d orbitals shrink in size. It is not about the cation or an ion. It is about the share of electron pair which is being pulled towards either a highly electronegative or a highly electropositive atom. Okay, it is not about cation or an ion. It is about the electronegativity. Which is more electronegativity, it will pull towards itself. Okay, still have any doubt? Okay. Please explain about its bond pair XeO2. Sorry. XeO2. Whenever you have oxygen in the molecule, always consider it to be a doubly bonded, until unless it is bonded to something hydrogen or chlorine. Suppose if I am talking about HOCl, what should be the charge on sorry, if I'm what should be the central atom? Sure. What about HOCl2? Okay, let's drop it. H2SO4. In this you have 4 oxygen and 2 hydrogen. That means it is very much clear that the 2 oxygen would be singly bonded to sulfur and the rest are doubly bonded. So if I am talking about sulfur, it would have 6, okay, plus I am talking about I will take only singly bonded, that means 2. I will not take the oxygen which are doubly bonded. Similarly, when I am talking about XeO2, there is no hydrogen. So I will take only the outermost electrons of xenon 8 plus I am not taking this participation, I will take it as 0 divided by 2 gives 4. Okay, then the ideal shape should be a tetrahedron, right? But since there are only 2 bond pairs, 2 atoms available, it would be XeO2 with 2 lone pair, because out of 4 there could be only 2 bond pairs and the rest 2 are lone pairs. Okay, clear? Any doubt? NO2 minus. What is the number of outermost electrons? 5. These oxygen are doubly bonded or singly bonded? I don't know. You know, this is minus, so you have to take into account 1 divided by 2. It would be 3. Ideally, it should have a trigonal planar shape. That means nitrogen with oxygen, right? But this is, the rest should be a lone pair and the other is a double bond. Sorry? ICl4 minus. ऑक्सीजन का 1 charge is there. जब भी आपको लगे NO2 माइनस, इट इज़ लाइक अगर मैं NO2 माइनस को एक न्यूट्रल स्पीशीज बनाना चाहती हूँ, इट वुड बी लाइक HNO2. सो नाउ आई कैन एज्यूम कि नाइट्रोजन के साथ एक डबली बॉन्डेड ऑक्सीजन होगा और एक सिंगली बॉन्डेड. सो जस्ट एक बार इमेजिन करो कि ठीक है मेरे पास एक सिंगली बॉन्डेड है और एक डबली बॉन्डेड है, उसका जस्ट मैंने हाइड्रोजन रिमूव कर दिया, इसीलिए 5 + 1 डिवाइडेड बाई 2. इट वुड बी बेंड शेप्ड. ठीक है. Yes, sorry. What you were asking? ICl4. It would be 7 + 4 divided by 2. ICl4 minus हो गए, right? 7 + 4 + 1 divided by 2, right? That means it would be 6. It should have what kind of structure? Octahedral, but ICl4, right? Rest would be 2 lone pair minus. That was only the case for trigonal bipyramidal. Okay, because here it would try to attain symmetry. Symmetry is also very important.
So ma'am, if it needs to choose over stability and symmetry, which will it prefer? Like for the
For trigonal bipyramidal, it would try to attain stability, and for octahedral, it would try to attain symmetry. Okay, clear?
yes, ma'am.
Thank you.